Hello everyone, my name is Yushan Pan. This presentation is about our latest work, Routability-driven global routing with 3D congestion estimation using a customized neural network. This work is done by me, Zhonghua Zhou, and Professor Andrei Ivanov. The current digital flows are quite modular, and EDA is an essential tool which is used in almost all the procedures in the RSI design. So usually EDA is divided into two halves, the front end and the back end. And for back end, we usually have floor planning, placement, and routing. And in routing, we have global routing and detailed routing. And among so many procedures, routing is one of the most important and time-consuming ones. In industry, it may take days or even weeks to finish routing. And even after spending so much time on routing, it still can fail due to the design rule violations. So what if we could predict the results of routing before routing takes place? So maybe we could avoid wasting time on unroutable designs or even improve the performance of current routers. Before we get into our work, I need to explain what is global routing and detailed routing and some terminologies that are used in our presentation. The difference between global routing and detailed routing is mainly in their resolutions. Detailed routing has a much higher resolution than global routing. And global routing sets a boundary for detailed routing. For example, let's say we have a very simple design and it only has two pins. And by pin, I mean the pin of a standard cell, and it's the physical connection of a standard cell. And we want to connect these two pins by a wire. And what we do in global routing is that we put a grid on this design and divide it into 4 tiers, which we call global cells or G cells. And in global routing, we set an approximate route for this wire, and we determine that it goes through these 3 G cells. And in detailed routing, we put a finer grid on in this boundary, and we set the finer route for this wire. And there are some terminologies need to be explained. The first, capacity. Given an age, for example, this age, the capacity of that age is the maximum number of wires or vias that can go through that age. And we have demand, which is the actual number of wires or vias that can utilize an age. And for take this age, for example, the demand of this age is 1 because there's only 1 wire going through it. And we also have overflow. It happens when demand is larger than capacity, and it equals demand takes away capacity. And if demand is smaller than or equal to capacity, it's 0. So this is the workflow of our work. What we did was that we predicted the global routing condition based on placement information and used the predicted results to improve the performance of a global router. First, we used a hyperimage generator to extract features from the placement information, which is a netlist, and map them into a hyperimage. And our proposed global net can predict the condition based on the hyperimage and generate some congestion heat maps, which describes the congestion level of a design. And our UBCGR can utilize this congestion heat map to get the routing results. Our contributions are mainly in 3 parts: 1, feature extraction algorithm; 2, a congestion predictor; and 3, a global router. And let's get into the feature extraction method. So to do feature extraction, we need to map a design into a graph first. And to do the mapping on a two-dimensional design, which only has one layer, it's very simple and straightforward. We put a grid on this design, and each tire is a G-cell. And here we have a graph. So each vertex is a G-cell, and there are edges between adjacent G-cells. And let's say we have a pin in this tire, in this G-cell, and a pin in this G-cell, and we use a wire to connect these two pins. What's going to happen in the graph is that the pins are on vertices, and the wires are on edges. And this is how we do the mapping on a 2D design. However, most modern VLSI designs are three-dimensional, which means they have more than one layer. So our graph also has more than one layer. And each vertex is a G-cell, and an edge between two adjacent vertices on the same layer is called a wire edge, and an edge between two vertices on different layers is called a via edge. And we also need to do a feature extraction based on the graph. So we have 7 features in total. The first choose are wire capacity and via capacity, which were introduced in my previous slide. And we also have pin density, which is the number of pins in a G cell. For example, the pin density of this cell is 1 because there's only one pin in this G cell. And we also have neighborhood pin density, and we have net density, which describes the density of wires and is calculated by Rudy algorithm. And we have local net density and global net density. So a local net is a net that has all its pins in a G cell. For example, this blue net is a local net, and we have global net, which is a net that has at least one pin in a G cell and at least one pin outside that G cell. Now we know how to do the feature extraction, but we also need to map the features into a hyperimage. And the way we do that is that we use a 2D array to represent a feature. For example, for this design, we use a 4x4 array to describe the pin density of each tire, and it's going to be one channel in the hyperimage. And then we do the next feature, like we can do neighborhood pin density, and it's another channel in this hyperimage. And we do this for all the features in this design. And in the end of the day, we are going to have an image with multiple channels. The number of the channels is related to the number of features and the number of layers in this design. Now we have a hyperimage, and what we are going to do next is that we want to predict the condition based on the hyperimage. We used a convolutional neural network to do the prediction. But one problem about CNN is that the input size and the output size are preset, but the size of hyperimage and condition heatmap are not. So to solve this problem, we use a strategy called windowing and sliding. So we put an input window on the hyperimage and take part of the hyperimage as the input, and the output is also a part of the entire condition heatmap. And once a prediction is done, we slide the window to another location and do the prediction again. And we repeat this procedure until the output window covers the entire congestion heat map. This is the network structure of our proposed global net. On the left is the input window, and on the right is the output window. N is related to the number of features and number of layers, as I mentioned before. And M is related to number of layers only. As you can see, we used FCN, fully convolutional neural network, to do the prediction, mainly for two reasons. Firstly, it's simple, which means it has the fewest number of parameters and fast to train. And secondly, it can keep the spatial information of the input. The difference between FCN and the traditional CN is that traditional CN has fully connected layers, which disarrays the input into a vector and then reorganize it to our output, which is a congestion heat map. However, FCN doesn't have to disarray the input, so it can keep the spatial information to the greatest extent. And intuitively, the congestion of our output window is highly related to its surrounding tires. So that's why we need to keep the spatial information. And this is an example of our predicted congestion heat map. On the left is the prediction, and on the right is the ground truth. And in these two images, each pixel is a G-cell, and the brighter it is, the higher congestion level it has. And we chose this image because it's very typical. It's one of the largest and most complicated design in our benchmarks. And as you can see, the overall brightness are similar, which means the predicted values are very close to the actual values. And also the patterns are similar as well, like the ISPD pattern in the middle. So this part is the most difficult because they are all zeros. And for some predictors, they may generate a lot of noise because there's not much information for the predictor, but our predictor can predict it very accurately. We not only did congestion prediction, we also proposed a global router that can utilize the predicted results to improve the performance of routing. So what we did was that we improved the cost function of CUGR, which is an open source global router. The cost function of original CUGR is like so. It's the wire length of, so this is the cost of an edge between vertex U and vertex V on L's layer, and it's equal to the wire length on this edge. So this cost function is actually simplified due to the time limit of this presentation. If you are interested, you can refer to the CUGR paper and our paper. And what we did was that we add another term, estimated overflow, to the end of the CUGR cost function. And this estimated overflow is related to the predicted congestion. The higher congestion, the larger estimated overflow, and the larger our costs. And in UVCGR, every time it does routing, it always chooses the route with the lowest cost. So by doing so, it can avoid routing through those tires that have a high congestion level. And experiments have been done to test our UBCGR and GlobalNet. We implemented GlobalNet using TensorFlow framework, and we used CUGR as the baseline algorithm for UBCGR. And ISPD 18 and 19 benchmarks were used for both routers. We first tested the performance of GlobalNet. Two metrics were used to evaluate GlobalNet, PCC and NMSE. PCC is a correlation coefficient which measures the linear correlation between estimated values and actual values, and NMSE is the normalized mean square error, which describes the difference between estimated values and actual values. And these two metrics are widely used to evaluate the performance of a predictor. As you can see in the table, listed here are the design names. So there are 18 designs in total, and these are the average of the results. And we have a very high PCC and a very low NMSE. A high PCC means the actual value, so the estimated values and actual values are highly related. They have a same pattern. And a low NMSE means these numbers are the estimated values and the actual values are close to each other. So in other words, our prediction is very accurate. We also tested UBCGR and compared it with CUGR, and three metrics were used: Y length, number of fields, and number of overflow. And these numbers are average numbers of 18 benchmarks, and it's been normalized. As you can see, our UBCGR successfully reduced the number of fields by 3% and number of overflow by 15%. So we believe that by predicting the condition of a design before routing takes place, our UBCGR can avoid routing through those tires which with potential congestion, and that's why it can reduce the number of overflow by such many. And if you still think it's not a huge improvement, please keep it in mind that CUGR is already a very good global router, and ISPD benchmarks are not so hard for it. So among all these 18 benchmarks, only 3 of them had overflows, which are 92, 99, and 9010. And for all these 3 benchmarks, our UBCGR reduced the number of overflows of them, especially for 99. CUGR had 99 overflows, but our UBCGR had 0. So having that many overflows means that it may be unroutable for detailed routing, because it may end up with design rule violations. And in this case, you're going to have to do the placement and global routing, detailed routing all over again. And you may need to do it iteratively until you have a valid solution. And it's very time consuming. But our UBCGR, so we reduce number of overflow to 0. And it's not about improvement. It's about making a thing which is impossible for CUGR possible. So we can say that it's a huge improvement for this benchmark specifically. And we believe that the more complicated the design, the better improvement we are going to have. And here are the conclusions. First, we proposed GlobalNet that can predict the 3D congestion information based on benchmarks placements. And we also proposed UBCGR that can perform 3D routing, 3D global routing with the congestion heat map. And we improved the global routing performance on the latest ISPD 18 and 19 benchmarks. And our future works will be focusing on the detailed routing. We will try to predict the detailed routing design rule violations and use the prediction results to improve the performance of detailed routing. And finally, thanks to National Science and Engineering Research Council of Canada and Huawei for their support and funding.